I didn't share my screen. It's visible, right? This is visible, right?
It's coming up. It's coming up.
It's visible, right?
I can see that. Yeah. Right.
You have any doubt you want to ask? And we'll start.
No, I think we can start on this. I will also just go through the. I think this time I could solve that questions, most of the questions in time. Let me just check it out if I have some. Oh, I think I was able to do it, but let me just check it out. In week 10, right? Okay. Yeah, I think I will come back on this, but
So,
this first question, yeah.
what was discussed in week 10 was line search methods were started. And so, line search is basically for unconstrained optimization. You one second. For line search, which is an unconstrained optimization, where you have some minimize fx x in Rn, and what you try to do is uh, at every you start with some x0, some initial point. I think they use subscript x0, and then from each xk you choose some direction pk, and this is step size, and you get next iterate. So as you keep doing this, you will get a sequence of xk, and you want to choose your alpha and pk such that this xk, the sequence, it should converge to some x star, and this x star should be the minima. This should be this r min f of x. That is what we want. So line search is like a way to choose this alpha if you know which is a good direction to like take a step in. And one good direction to take a step in is pk uh, equal to minus gradient of f of xk, which is the steepest descent direction. And so there were some conditions which were written for what a good step size is via Wolf condition. And other than that, I think there was some discussion on rates of convergence, how it is dependent on the condition number of the Hessian in the quadratic function case. and then Newton's method, and then there was a discussion on constraint optimization, in which you make use of a penalty function to make the constraint optimization into an unconstrained optimization. So you have some f of x, which is the objective, plus c times p of x, which is a penalty function. And I think what is done is this penalty function depends on your constraint, depends on constraint, which defines your feasible set S, and you choose some ck plus 1 greater than or equal to ck. C is a constant, and you keep doing this, and you minimize this function fx c ck, so you'll get a corresponding some xk argument, and this is sequence xk, this converges to x star. This is the theorem. I think its proof was not discussed.
Hmm. How the actually the CK sequence gets created? Uh, I mean, how CK plus 1 is created from a CK? I know it will end up with the infinite, right? How?
Yeah, so it basically you just choose, you keep choosing some value bigger than the previous one.
Okay, okay. So there is no as such a rule, a particular value, right? I mean, it is not driven from a step as such, right?
No.
Okay.
So I just collected some questions which are from some 2022 assignment of week 10. So in this question they are asking, they are given some objective function, and they are asking which of the following is not a descent direction for f. So descent direction should mean, if d is a descent direction, then
Derivative, yeah. Take a derivative, find out that point, find out the angle between them, right? So basically, do a cross product. It should be a positive. If it is positive, it is a descent direction. No, it is ascent direction,
yeah, yeah.
right?
So we need descent means dot product should be negative.
Yeah, yeah.
So this gradient, this should be less than that. So if you look at this fxy, this will be something 10x,
Plus 2y.
and the rest is 0.
Yeah.
So 2x plus 6y.
Plus 1.
Okay, and at
3. 0 and 3. 6. This was 0, 19, right?
yeah.
Okay.
So we just need to check
1 minus 4.
dot product with each. So
First term is a negative, I guess.
this is 9.
So minus 6, minus 6, minus 13. Minus 6 plus 19 is 30. Last one.
So we are asked which is not a descent direction. So this is not a descent direction.
No, no, so yeah, just one quick question
Yeah.
on not exactly on this, but this Lipschitz function, right, which is used to find out the strong wolf condition, right? So the basic concept of wolf condition, I mean, of Lipschitz function is that the change in the function value and the ratio of a change in the function value and the ratio of a change in derivative values, right? So, I mean, what's more of an intuition of that? Mm.
Uh, like for those kind of functions, there's a lot of theoretical
Okay,
sort of uh,
okay,
like convergence proofs and all. They are very popular for those kind of functions. They're well studied. They have some good properties, I can say. The
okay,
gradient change is upper bounded in some sense.
okay. So that will, yeah, that will help us to find out that the maximum slope, yeah, alpha slope, uh, it will help us to find out. It will ensure that the slope is not so low, right? Type of things, and hence we can restrict it to the higher level of slope. That's what it tries to do, right? In a strong condition.
Uh, Strong wolf condition, we are not really using the. Are we using Lipschitz condition?
Yeah, yeah. So Lipschitz is probably used in a strong wolf condition. Uh, so my understanding. Do you have that? Okay. Do you have any chance that particular slide also? Or I will also search it out. I would have downloaded it.
1 second, I'll just download it.
Probably it was covered in the Lipschitz was covered only in that case.
I think it is covered in the convergence part, na convergence of if it satisfies Wolf condition and the gradient is Lipschitz continuous.
Hmm. Okay. It's cool. Acha, so it is not directly used out there, is it? Somehow
So
thought
for
so.
convergence proofs, if it is if it this satisfies, then you have a good proof.
Oh, okay, okay, okay. Oh,
So
okay. That's no plus, right? Suppose the belt is so.
so when this condition is satisfied, then you get this condition.
Okay, so basically it helps in conversions actually, yeah.
Yeah, because this is like uh, this x minus some some x bar is like your iterates now. You
Yeah,
are
yeah,
iterating how much the gradient is changing.
yeah.
So as it starts to converge, the gradients should not change very much.
Okay, okay, okay. So change in the derivatives should be uh, 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 yeah, it can't be bigger than a yeah by changing the values at some time when they are closed. Yeah, that's the intent. Okay, good. Yeah, I understood. That makes sense. Makes sense. Thank you. Take a derivative of these. Steepest descent, right? So 2x and 4y are the derivative of a function. So uh, 2x and 4y. So at 3, 2, it is equal to what? 6 and 8. Delta fx is 6 and 8, right? So then we have to do a minus of that, right? So what is the point? 3, 2. So it is 3, 2 minus 6 into zero point 0.2. That is what? 1.2. So 3 minus, yeah, zero point 0.6 into, yeah, zero point 0.2 into, yeah, 6 at 10, right? Yeah. So, yeah. So 1.2 is constant is 1.8 and
Minus
1.6 is gone. 2 minus 1.6 equal to 1.8 and zero point 0.4. Yeah. Oh, okay. So this is x1 only. Now we have to do x2. Okay. Okay. So now we have to find a derivative again. So which is 2 times this and 4 times this. So 3.6 and 1.6.
6.
1.6, 0.4 into 4, right? 1.6. And now we'll start with this point 1.8 and zero point 0.4.
Okay.
No, 1.8, yeah, 1.8 and zero point 0.4, right? We'll start with that. Minus zero point 0.2 into this 3.6 and 1.6. So it is 0.72 is gone. So it is 1.08. Yeah, 0.72. And zero point 0.4 minus 0.32. So 1.08 and zero 0.08. Yeah, C. Uh, yeah, I mean, 1 0 is not required, right? 1, 1.08 only,
Oh,
not
sorry.
yeah, that's, yes.
So this kind of because usually we just use directly solvers.
Yeah, yeah, yeah. We never actually completed, right? So actually, as part of this assignment, I did one. Actually, this Newton-Raphson method is solved for some iterations at least now, after a lot of many years.
But to just verify whether your thing is working correctly, one iteration you can do on the solver and one by
Yeah,
hand and check whether.
yeah, yeah, yeah. Right.
Uh, okay, here we had only two variables. If we have any variables, then we can take.
Uh, suppose we want to minimize this function. Starting from again, we arrive at only one iteration using square method with exact line search. Ah, this should happen if it is a symmetric function and it is more of a circular type of things, right? And hence you should be able to do it in a single cut. So we have to prove that this is a, I mean, QS has to be a symmetric matrix actually, in that sense, right? Then it is a single cut, single step. No, is that right? I mean, is that?
Symmetric is may not be
I mean,
sufficient.
so if contours are like a circular type of things, right? Then only you will be able to do it in a single shot, no? Or there is there any more condition required other than that? Okay, I forgot actually.
Symmetric may mean like why are you saying symmetric is enough?
So what would happen with a symmetric, right? So uh, we are talking about steepest descent, right? In the steepest descent,
Steepest descent and exact line search.
exact line search, right? So okay, yeah. I mean that's what I thought that if it is more of a, circular contours, right? So the steepest descent direction has to go. It's a circular, right? So in some sense, it will be pointing to the center e- directly, right? That was at least the intuition,
Mm-hmm.
right? Because it is completely circular throughout, right? So how much steps you take, you are going to you are going to be at
Yeah,
any
yeah,
point you are always perpendicular to that tangent. So or basically, yeah, I mean, yeah.
yeah,
So
yeah, yeah. I got what
that
you're
is,
saying.
yeah, this seems to be that type of function, I guess.
Yeah, this will have circular contours.
Yeah, and hence it should work. That is the hypothesis at least.
Yeah, that is correct. Because you're saying a circular contour, so no
Yeah,
matter from where you start,
yeah,
the
you will
direction
hit.
will be towards this only.
Correct,
So
correct,
when you do
correct.
line search over here, it will directly give you this much step length.
Right, right, right. Yeah, that is at least the intuition. Yeah. And if you have to prove it more formally, then we have to take a derivative and show that it will reach there, right? I mean, that's the more formal.
Yes,
Or
yes.
so here it is a x1, x2, x3, right? I mean, that's the derivative. X2 is getting cancelled. I mean, so uh, x1, x2, x3 type of things. Uh, so at a given point, uh, yeah. Now let's assume that we started with some point, right? Which is a in some point, like ABCD whatever, A1, A2, A3, right? AM. We start with x0, which is equal to a0, a1, or something like that, some subscript n things, and then take a derivative of this, and
I think the closed form for line search was discussed
yeah, let me just, yeah, search it out. I forgot.
for a quadratic function.
Uh, Rate of convergence. Oh, so it is like that alpha is a what a derivatives. Yeah, that form, right? When derivative of fxk transpose into derivative of fxk upon that into q into that, right? That type of calculations we have to do.
Yeah, yeah, yeah. So alpha 0 will be delta fx.
transpose.
Fig 0 transpose q. This is f of x is a form half,
Half
x.
x tqx minus btx. Out of that, btx is anyway not required, right? So
Yeah,
so q
because it is.
here identity. So q here is identity, no?
Yeah, q is identity.
So that means alpha is equal to 1, is it? Is it? I think so. It is 1 only. Yeah, it is identity only. Yeah.
So this implies alpha is equal to 1.
Correct. So alpha is equal to 1. Get directly. Okay.
So
Uh,
x1 is equal to x naught minus alpha, which is 1, times the gradient is
same actually.
x1,
Yeah, it's 1 into x naught. Yeah.
so x1 is equal to 0.
Yeah. Right.
And 0 is the minima because it's all positive, so this will be greater than equal to 0.
Yeah. So is the general idea would be if alpha is equal to 1, then only it will be possible, right? Or will there be any situations where x0 is a something like a alpha is a 2, but whatever is the derivative, it will be that. I think it is possible, right? So we can find that out, I guess.
Yeah, I
Uh,
think it
it's
is
not
possible if you, I think if you remove half from here.
yeah, correct. Correct. So it is a 2x1 type of things,
Yeah,
and hence that alpha will become 2, right?
yeah, yeah.
Yeah. Yeah.
Uh, will it become? No, it won't become 2.
It will become.
Even if I remove half, still it will be 1 only, I think.
Okay, let's see. So if it is a 2x1 and all that type of things, so all these values come as a 2 type of things.
Yeah.
And alpha is still 1, right? So if it is 1, but then x0 would be uh,
Okay, here it will be 2 to 2. So alpha will be half or something like that.
okay, okay, okay. Acha, so q will be 2 types. So right. Right, 2x1 square, right? So yeah, so it is, yeah, correct. And that's where it gets cancelled actually, yeah, right. That's where the 2 of, yeah, delta of x and here half will get cancelled, right? Makes sense. Makes sense, yeah.
Yeah, so it will be 1 only, no?
Yeah, right,
Okay.
right. Same will be always 1, yeah. Because q will get double and hence alpha should be always 1. Yeah, and let me also try sometime later just to confirm.
Because here we are saying from any arbitrary initial point. Because if it is 2, it means like if, let's say alpha was 2,
Yeah,
then we are saying like from that point you reach some other point and then only you go to 0.
yeah, yeah.
So it will be 2 steps.
Mm.
So if it was not converging at 0 and some other point, then maybe we would require some other alpha.
Yeah, right. Uh, mm. So, I mean, that's fine. So, but if Q was for every symmetric matrix it will happen, or only if it is a diagonal it would happen to the one step.
Sorry, what are you saying?
So here Q, I mean Q was a diagonal, right? And first we check it is one, then it is working. If Q is even 2 to 2, which is still a diagonal matrix, it will work. But will it work for every? I mean, does it? Is the mandate is to have a non? I mean, mandate is to have a diagonal matrix only to have it in one step, or that is also not required. No? If a Q is a non-diagonal matrix, then also is there any condition by which it can happen in a single step, or it would never? That's it.
Q is non-diagonal.
Q is a non-diagonal. Will it guarantee any time that it is a under any condition it will happen in a single step? Just a step. Uh, it may, yeah, it may be still possible, I guess. It is still possible, I guess, right? If it is symmetric, it may be still possible, I guess. I'm going to check it. Yeah, I will check.
I think that circular contour idea that should hold.
Correct. So that we'll have to check it out, right? So it means for us even symmetric, it should be still circular. So this is right or okay.
So this is okay. So uh, a sequence is given and we are asked the rate of convergence. So the rate of convergence was defined as delta over from 2 to 1 linear quadratic greater than 2 to 1 and this some constant times is 0, then check the rate. So here the limit of the sequence is it's sk, which is equal to 1 by 2k. Limit of the sequence as k tends to infinity is 0, right? X star is 0.
Yeah.
And we can check when k tends to infinity, 1 by 2k plus 1 minus 0 upon 1 by 2k minus which is half,
No.
and this is less than infinity. So we get for beta equal to 1,
Okay.
and if beta is equal to 2,
So
then either 1 by 2k plus 1 upon 1 by 2 power 2k, right?
yeah, right. Equal to 2 raised to 2k upon minus 1. 2 raised to k minus 1. So it will be infinite.
Is k minus 1.
It will be 2 raised to k minus 1, no? Not 1 upon, right? Because 2k will come
Yeah,
on the new
correct, correct. 2 power k minus 1. So this will be infinity.
infinite.
Correct. So it is not quadratic. So we can say it is linear.
Yeah.
We have some function. We are minimizing using steepness descent. Alpha k equal to 0.54k. Is where how many iterations are needed to converge to optimal solution exactly.
I think the execution seems to be a. It will take infinite. Right. No, I mean, this seems to be again that completely circular type of things.
Yeah.
So if alpha equal to 1, it would have taken in the one step. But as we are reducing the step size, it would be, I mean, it will be continuously zigzagging. That is a hypothesis. Or it is not. No, actually, not.
Won't zigzag.
Hmm.
Hmm.
Yeah,
Won't
it is not zigzagging, right? Because, yeah, because it is still circular. So it will still go in the same direction.
yeah.
Only thing that it will take every time smaller and smaller steps.
Yeah. So it will only go
No,
if it is
not a
here, then
zigzag.
it will go only half distance.
Yeah.
Then from here to here, it will again only go half distance. Half distance. So there will always be some half distance left.
Yeah.
So
Right,
it
right.
won't converge exactly.
Yeah. Yeah.
But it will become very keep going closer to it, but never actually reach exactly to zero.
Right.
So this is infinity. So from 1 comma 1 we'll go to half comma half, then 1 by 4 comma 1 by 4, then it is 1 by 2 power k comma. we get infinity, is this will be equal to 0.
Right.
So there are two statements, and which is true and which is false, we need to say. Each iteration of Newton's method is computationally heavy than each iteration of steepest descent method. So
Probably true, right? Because it requires second derivative.
yeah, and the inverse of it.
Oh yeah, right. Right.
You need to compute the inverse of a matrix.
Hmm.
So this is correct.
Is faster than this seems to be false. I think Newton method will be faster.
The third requires inverse calculation. Convergence rate of steepness. You're saying Newton. Yeah, correct. Newton's method is faster. So this is incorrect.
It's false. So it's false.
So this has a linear convergence rate. This has a quadratic. Okay, I'll write the option. Uh, g of x equal to e power x is 0 to 0. Sorry, 1 minus e power x. Hmm. Options will be so so we need to find the penalty function. The penalty function is this penalty function. So p of x, the conditions where it should be continuous, and p of x is greater than or equal to 0 for all x, and p of x is equal to 0 imply that x is in the feasible region, and x is in the feasible region should imply p of x is equal to 0.
Yeah. Just one point, right? So basically, a penalty function is also dependent on the sense of the function, right? If it is a minimum or maximum, should be right.
No, it is just to define the feasible region.
Okay, it is always in the physical region. Okay.
Yeah.
Oh, okay. Uh,
Whenever the point is in the feasible region, this is equal to 0.
oh,
The
yeah,
penalty
correct.
function is equal to 0.
In the feasible region, point has to be zero. And for other thing, it should be either positive or negative. It is okay for now, is it? Because I thought that it would depend on if it is positive or negative, right? If it is minimizing or maximizing, then some numbers will be acceptable, right? Because if it is
Okay.
minimizing, right? So
Yeah,
then
that we
you're
can
okay to
change.
accept max one, right? I mean, because in fact, I think you got my point, right? If it is
Yeah,
in
yeah.
the other situation, it is still helpful. If it is not feasible, right? It will.
The way we defined it, it was for minimizing
Yeah,
type
yeah,
of
correct. So
things.
let's assume that this is for minimizing checks, right? Yeah,
Yeah,
good.
yeah.
Okay.
So we just need to check these all functions seem continuous, right?
Right.
I think these are not continuous. Okay, these are also continuous only.
Uh, yeah. So e raised to x is equal to 0. E raised to x can become. Oh, correct. 1 minus e raised to x should be a. It can come to negative. It can come to the. 1 minus e raised to x can be a negative number if x is a very high number, right? So very high number is not a because we expect gx to be greater than 0. So
Yeah, so basically we want this should be greater than equal to 0.
yeah, so that means 1 is greater than ex. So x has to be less than 0. I mean, x is less than 0 is our physical set actually, right?
Yeah. So this means e power x should be less than equal to 1. That means x should be less than equal to 0.
Yeah, right. That is only the physical set. And we are to add something into this function. We are trying to minimize the function, right? So anything out here which we provide, it has to be a positive number. Then it is a good penalty function, right? Because we are minimizing. So we have to have a, it's a plus ck, right? Type of things. So if a number is added as a positive number, a big positive number, it is good for us, right? No? Is that an intuition, right?
If x is greater than 0, then we add some positive. That what you
Yeah,
mean?
right, right, right. If x is greater than 0, this number has to turn out to be a positive number, and then it is a good function,
Yeah.
right? So if x is greater than 0, so let's assume that x is equal to 1 for simplicity, right? So max 0, 1, yeah, it seems to be a good one actually. It is a positive number. Right? So B seems to be okay, I guess.
Yeah. But
Right?
whenever x is less than equal to 0,
Yeah, it is
it is
0.
0.
Yeah, and x is greater than 1, it is a positive number, which is good.
Yeah.
Third one is x is equal to 1 if I assume then 1 minus e and 0. The minimum of 1 minus e and 0 is 1 minus e. But taking a sign of that is a e minus 1. So that should also be okay. C should be also okay, I guess.
Yeah.
Right? Because it should be still okay. Fourth one is a max of 1 minus e and 0. It is a 0. No, that is not good. So D will not satisfy.
Yeah. Same.
It doesn't satisfy. First one is a 1 minus Ex. You're saying absolute time of that, right?
Yeah, this is absolute.
Absolute is a absolute should be okay. Absolute should work out. That should also work out.
Here there's a problem, right? Because this is zero only when x is zero.
Uh, X is one. No, X is zero. It will be zero. Right. Right. Absolutely. Yeah. Otherwise, it is not a zero. Correct. So we want to have it zero for a feasible set.
Yeah.
So it is not a zero for feasible set. Yeah. Makes sense. Makes sense.
So this is also right.
Yeah.
So these two are correct here.
Hmm.
Okay, so this is our earliest discussion, right? So maybe I'll just discuss one more question.
Yeah. I have to drop in 5 minutes or so, but yeah, we can.
Okay, okay.
Sorry, I had to join that call.
I'll just discuss one question and mm, for steepest descent, this exact line search show pk plus 1 is orthogonal to
Okay.
pk for ortho. Okay,
Hmm.
so we need to just show that when you are doing steepest descent with exact line search, uh,
Hmm.
when you're doing steeper descent, basically your pk is negative of the gradient, right?
Hmm.
And your next iteration pk plus 1 is negative of the gradient at that point.
That one X1 plus one. Okay.
So we need to show this basically. So this orthogonal means pk is transpose
PK plus one. Yeah. Equal
pk
to
plus 1
zero.
is
Yeah.
equal to 0. So that means this transpose plus 1 is equal to 0.
Hmm.
So, and this is happening when you do exact line search.
Hmm.
So exact line search means you have xk plus 1 is equal to
Hmm.
xk plus
X alpha into.
pk.
Hmm.
I use some subscript here and there.
Okay, come on first. Yeah, alpha we already defined, no? For exact line search. Yeah,
Yeah,
we
so
can.
for an exact line search, what we'll have is uh,
Alpha should be uh, something like a delta.
yeah. So if we have some f of uh, alpha k,
Hmm.
then alpha is such that uh, this is zero, right?
Huh. Right.
So that means this one, alpha f of xk plus alpha k pk. So if you do the chain rule, what you'll have is gradient at uh, xk plus 1, right, times
Uh, how we are I think I remember what I forgot. We converted f of alpha. F of alpha is same of above f function, and because
Yeah.
f is function of x, right? In the sense, so how we
So this is basically
uh,
xk plus 1 is xk plus alpha k pk, right?
huh,
So at xk plus 1 we can redefine this as f of alpha.
oh, okay, okay, okay. Yeah, because xk is known actually. Yeah, right.
Maybe you can put k
Yeah,
here.
yeah, yeah. Fk of alpha. Okay, yeah, right. And that makes sense. Okay, so
So here also we can put k. So if you do this, here you can use chain rule. So this is basically this by del alpha xk plus alpha k pk. I think I should drop k here, because where it is 0 there we define your alpha k.
yeah,
So this is basically f of xk plus 1, and here you will get pk, and pk, if you are using steepest descent, then pk is xk negative.
huh,
So if we are setting this to 0 means this is equal to 0. Here it should be transpose actually. So we get,
yeah.
and this is
Next,
true.
next.
So this was the condition for line search. You choose your alpha such that this is equal to 0,
Hmm.
and this is the condition that pk is equal to this, that is your steepest
So,
descent.
yeah, makes sense.
So in
Hmm.
case of that circular kind of thing,
Yeah,
because it is straight, you can't take next step orthogonal, directly you reach the center.
yeah, right, right. That's another. Correct, correct, correct. That's a corollary about it. Right, right. And that makes sense actually why it should be. Yeah.
Yeah.
That's more good solid intuition. Yeah. Yes. Thanks, Pranav. I have to drop off. I will try to join back at 7:30, but I don't know if we are going to continue at that time. Or...
No, actually, this only these many questions I had.
Okay, okay. That's fine. That's fine then. Thanks. We'll connect again next week.
Yeah, yeah, sure.
Thank you.